Good morning, class. We are looking at the last module, Module 5, covering chapters 10, 11, and 12. Chapter 10, Correlation and Regression. Chapter 11, Goodness of Fit and Continuity Tables. And Chapter 12, Analysis of Variance. And 4, now we're going to look at Chapter 10, Correlation and Regression. So we're looking at Chapter 10, Correlation and Regression. And we want to answer these questions. Could somebody read this question for us, please?
Given the sample data, find the value of the linear correlation coefficient, R. Test the claim that there is a linear correlation between the two variables x and y. Use both A method 1 and B method 2. Alpha equals 0.05. Find the regression equation and find the best predicted value of, hold on. Oh, I can't move you out the way. Of y at when x is, and I can't see the last one.
Is equal to 2. Perfect. Thank you so much. All right. So first, let's discuss the concept, scatter plots, and the strength of a linear correlation R. A scatter plot is a graph of the ordered pairs x and y. X is the independent variable, y is the dependent variable. So when we look at this one, which has a positive correlation, distinct straight line or linear pattern, we say that there is a positive linear correlation between x and y. Since as the x values increase, the corresponding y values also increase. If there's a strong positive linear relationship between the variables, the value of R will be close to positive 1, normally 0.7 or larger. Negative correlation. Can somebody read this, please?
You read B?
Yep, B, please.
Okay. Distinct straight line or linear pattern. We say that there is a negative correlation between x and y, since as the x values increase, the corresponding y values decrease. If there's a strong negative linear relationship between the variables, the value of R will be close to negative 1.7 or smaller.
Perfect. So, and if we look at this last part, there is no distinct pattern, which suggests that there is no correlation between x and y. So a couple of interesting things. So no relationship, no correlation. The value is close to 0. As we get away from 0 and get closer to 1, it's a strong relationship and it's positive. As we get closer to negative 1, it is still strong, but in the negative sense. Correlation doesn't imply causality, meaning if there is a correlation, doesn't mean it causes it. It is the one that resolves that. So we are looking at question 1, part A. Find the value of the linear correlation. First and foremost, nobody expects you to do this by hand. You can do it with technology. However, for this one, which we have 1, 2, 3, 4, n equals 4, it's small enough I can, show you how the calculation works. Okay, and I'm going to go over that. As you look at this formula, this is a very complicated formula. R is summation of xy minus summation of x times summation of y over the square root of n summation of x squared minus summation of x quantity squared times n summation of y squared minus summation of y quantity squared. Which means now, if we write this as x and y in a column. We need to calculate x times y, x squared, and y squared. So how do we do that? X times y, 1 times 2 is 2. 1 times 8 is 8. 3 times 6 is 18. 5 times 4 is 20. So that's how we calculate this one. How about x squared? Just square this one. 1, 1, 3 gives you 9, 5 gives you 25. Y squared, 2 gives you 4, 8, 64, 6 squared, 36, 4 squared, 60. So you have to do this one by one. And again, since n is 4, it's small enough we can understand. Now let's add them up. 1 and 3 and 5, they add up to 10. This is summation of x. This is summation of y. This is summation of x times y. This is summation of x squared, summation of y squared. Now we're going to put this into this formula. R equals n, which is 4, summation of x, y. This one, 48, minus summation of x times summation of y, 10 times 20. Divided by square root of, again, n is 4, summation of x squared, 36, minus summation of x, 10 squared. And this one, n is 4, summation of y squared, 120, minus summation of y, 20 squared. So I hope you see that, and you can distinguish between summation of x squared and summation of x quantity squared. This is different than this. Don't mix them up. You put it into a calculator, you come up with the answer. Again, no one expects you to do this by hand. So if you were to put this into a calculator, first you have to put it in L1 and L2. In L1 goes X values, in L2 goes Y values, for example. So first, stat edit clear list L1 and L2. So you put first and foremost in L1, 1135, in L2, 2864. Then you run the linear regression t-test. When you do that linear regression t-test, you go to stat test linear regression t-test, you enter L1 and L2. You don't touch anything else. And as far as this one, you choose not equality. And it gives us some value. It gives us a lot of information. For now, this is the one, and as this arrow meters go down, this is what we need. So if I stop here, 4 changes to 5. So negative 1.3, negative 0.135. Again, you don't have to do it by hand. Needless to say, it has a lot more information than just that. But I just wanted to show you one by one what it gives you. And of course, here's some statistical calculators. You can find this under module 0 of MOM. Under module 0 of MOM, you find many different calculators. I want to do the test of hypothesis. And the way the test of hypothesis works for a linear correlation is that you want to test the claim that there is a linear correlation between the two variables x and y. You're going to use two methods, and I'm going to discuss the two methods. As always, I'm going to go with 4 steps: null and alternative hypothesis, calculate the test statistic, go with the CV, critical value, and then make a decision. So these are the 4 steps. I would always do that and then answer the question accordingly. So starting with the null and alternative hypothesis, H0 rho equals 0. Rho is the Greek letter that represents correlation. H1 rho is not equal to 0, which makes a two-tailed test and it makes it the claim. I want to make sure we understand what's going on here. First, we wanted to find a linear correlation. Then we want to test the claim that there is a linear correlation. There is a linear correlation. And what happens is that when rho is 0, that means there is no correlation. I hope you remember when we discussed in the first page, no linear relationship, no linear correlation was close to 0. And if it was close to +1, had a strong positive linear relationship, close to -1, strong negative linear relationship. So that's why this means there is a correlation. This means there is no correlation. Now, here's the formula for the test statistic. Degrees of freedom is n minus 2. So for the first method, we use the t-test, and it's a two-tailed t-test. Here's the formula. What I want you to notice, this formula is the same as this formula, okay? Notice n minus 2 is at top 1 minus r squared. Please understand these two are the same. Again, this is elementary algebra. These two are the same. And as far as mu sub r represents the rho, and it always comes from H0, which is 0. But I'm writing the different formulas for you so you'll be exposed to both. All right. We already know n is 4 and r is negative 0.135. So we got to plug it into this formula. These two are the same, everybody. You do the math, you end up with negative 0.1927. For the second method, which uses the Pearson correlation coefficient, just the value of r, or this one, just the value of r is your test statistic. Continuing with this method, method 1, you go with the t-test. Alpha is 0.05, degrees of freedom is n minus 2, so 4 minus 2 or 2. Using a table, we get plus minus 4.303. You can even use a calculator. What about the critical value for this case? You have to use n equals 4, alpha equals 0.05, and what is called a Pearson correlation coefficient table. I have that among the tables that is posted on campus. From the table, and I will show you in the next page, both of them. From the table, you get this value. So I will show you how to get that in a moment. Now, all you have to do, graph this. This is a two-tailed test. So you have two tails. Alpha is 0.05. If you look at this one, alpha is 0.05 divided by 2 on each side. This is negative 4.303, and this is positive 4.303. If you just look at this one for now, this number, test statistic, is between these two, and it's way into the non-rejection region. If you look at this case looks at this one. According to the Pearson correlation coefficient table, R is minus 0.950 and positive 0.950. And here's your test statistic, again, between the two numbers. It doesn't have to be to scale. So it puts you way into the non-rejection region. So you fail to reject H0. Okay, so a quick recap. This number is between these two. This number is between these two. And so if you are not rejecting H0, you're rejecting H1, and therefore the claim becomes false. And that means there is no linear correlation between the two variables. Now, if we go back to the technology, the previous page, we had this. We ended up with the following one of them when we did the linear regression t-test. And clearly you can see the p-value. Here the p-value, here's the p-value. First of all, the test statistic, look at this number. Is this one, of course, with a lot more decimals because they didn't stop at this number. But this is the same as this one. The p-value is way larger than alpha of 0.05. Fail to reject or don't reject a null hypothesis. Again, I want you to see that a better way to write it is fail to reject. But if you wrote don't reject, that's fine with me. But in some instances, they may be very, careful with that, and they want you to write fail to reject instead. I want to show you how we found the critical value for the t distribution as well as the Pearson. So here's the t distribution, and degrees of freedom. We remember alpha is 0.05. That's area in two tails, and degrees of freedom is n minus 2 or 2. Put these two together, and you get this number. And therefore, t is plus minus 4.303. So if you're using the t distribution and you're using a table, you can also use technology. Now, this table, and you can find it under modules in Canvas, where we have the tables. You can even look it up online. Pearson correlation coefficient R. N is 4. Alpha is 0.05. So what's the answer? 0.95, because it's a two-tail test plus minus. So this is how you find them. Plus minus 0.950. Regression equation. Again, I'm going to go over the process, everybody, but you don't have to do this by hand. I'll show you where we found that with the technology. We've already done that, but I'm reminding you of the value of n and r, and these are the values we calculated: summation of x, summation of y, so on and so on. So according to the formula, y hat is b0 plus b1x, or y hat is a plus bx, depending on the, text and the technology. They use one of those. The slope b1 is n summation of xy minus summation of x summation of y, n summation of x squared minus summation of x quantity squared. Y-intercept b sub 0 is y bar minus b1 x bar. Y bar is summation of y over n. X bar is summation of x over n. These are some formulas. So if we want to calculate b1, we use this formula. We have all the values, everybody. So we have n, which is 4, times summation of xy, which is 48, minus summation of x times summation of y, 10 times 2. The bottom is n, which is 4 summation of x squared, is 36, minus summation of x, 10 squared. So I use this formula and I calculate b1. So to calculate b sub 0, I need to calculate y bar and x bar. Y bar is summation of y divided by n, which means 20 divided by 4. X bar is summation of x divided by n. That means divided by 4. So this is 5. This is 2.5. Now I go to this formula and I say y bar, which is 5, minus b1. Now, when I put b1, I'm not going to put this. I'm going to actually use the calculator, their value, and then times 2.5. Now for the calculated value, I want you to see this is a rough estimate, but I'm using a lot more decimals here because you don't want to do the rounding in between. You want to do it at the end, and that gives you 5.455. And therefore, this is your regression equation. Again, n was 4, so it was sort of reasonable. We could do that by hand. You don't have to do this by hand. I remind you of this. If you go back, you see we found that. And basically, this is a plus bx. This is a and b. So take a look at this one. A is 5.4545. So if we stop here, it changes to 5. And then b, because it's a plus bx, this number. And again, if you stop here, change it to 2. So I hope you see that this gives rise to this equation. So you don't have to do it by hand. Find the best predicted value of y when x is equal to 2. In general, you look at the correlation. If there is a correlation, you plug into this. You replace the x with 2. If it's not, so no significant linear correlation, the best predicted y value is y bar. That's what we do. Y bar, we've calculated it to be 5. That's the final answer. So p-value, if we also, so that's y bar and we're done. Remember, again, remember the p-value if we wanted to. The p-value was large compared to alpha, and we did not reject H0. That meant no linear correlation. That's why we are choosing in this manner. Could somebody read this question, please?
A researcher is studying the effects of testosterone injections on different lab mice. She controls the concentration of testosterone injected into the mice and measures their metabolic rates. Analyze the following data set. Will you be running a correlation or a regression? A, find the value of the linear correlation coefficient R and test the claim that there is a linear correlation between the two variables X and Y. Alpha equals 0.05.
Excellent. Thank you so much. So we are going to run regression. Why? Since she controls, and that's really the key, the concentration of testosterone injected into the mice and measures their metabolic rates. Because of the controlling, it is a regression. Because remember, correlation doesn't mean causation, causality. But this one is regression. Now, the process is similar. Now, again, we have so many pieces of data. Okay, it happened to be, if you count 1, 2, 3, 4, 5, 6, 10, 15, 17, any 17. We're not going to do, you're not expected to do this by hand. So you have to do the test of hypothesis. First, what is the test of hypothesis? Rho equals 0, rho is not equal to 0, it's a two-tailed test. What is rho equal to 0? There is no correlation. What is rho is not equal to not equal to 0? There is a correlation. So what does it mean? Part 1, there is no correlation between the concentration of testosterone in mice and their metabolic rates. In this case, there is a correlation between the two, and that is the claim in essence. That's what we are checking. So we are going to put this into technology such as TI, Excel, Minitab, you name it. And when we run it, it gives us this table, gives us R squared. So we're going to hold on to that, and we're going to do the test of hypothesis with the information that we have here in the next page. So this is from technology when you run it. And so we repeat the same thing. We have the value of n, we have the value of r squared, and this table, and we'll see what each one means. First and foremost, the first step is H0, rho equals 0. HA or H1, rho is not equal to 0. Test statistic. T has this formula. We've run the technology, and that's the answer. You don't have to do it. It's been done. Now we can do the traditional method, or when we look at the technology, they have calculated the p-value for us, the area to the right of this number times 2. So the p-value is the area to the, and I hope you, I mean, you can see it's a huge number. So the area to the, just let's assume, so this is the area. This area times 2. Times 2. Why times 2? Because it's a two-tailed test, everybody. This area times 2. Is this given to us? Yes. This is the number. 1.5316 times 10 to the power of minus 15, which means from this decimal, count 1, 2, 3, 4, 5, go all the way to 50. So put 0, 0, 0, 0, 0. This is almost 0. It's less than alpha, whatever the choice of alpha may be. And the choice was 0.05, by the way. So clearly it's less than alpha. If we go with method 2, which is simply using R, here's the value of R, everybody. From Pearson, N is 17, alpha is 0.05. I showed you the table. It gives you these two values. If you were to draw a line, we have these two values. And this number, 0.9934, it's way into the rejection region. So whether you go with that or the p-value, this is almost 0. So your decision making would be reject H0 since p-value is less than alpha. Now p-value is 1.5316 times 10 to the power minus 15, and alpha is 0.05. So that's how small it is. It's almost 0, as I mentioned. So if you are rejecting H0, you are not rejecting H1 or HA. That means the claim becomes true. The claim is true. There is a significant linear correlation between the two variables. Therefore, we conclude that there is a significant correlation between the concentration of testosterone in mice and their metabolic rates. Since this is a regression study, the significant slope suggests that the increase in concentration of testosterone in mice causes increase in their metabolic rates. What do we mean by significant slope? Here's the significant slope, everybody. This is the slope. I'll show you in the next page. So this and the usage of that. Significant slope refers to this number. By that, we mean a positive slope. It's a positive relationship. This R is positive. This is positive. Significant slope. This is positive. It's almost 1. Remember that. When it's close to 1, it's a positive. All right. Now, same question. Want to find the regression equation. Remember we had this. This is the intercept. Those are the coefficients. So y equals mx plus b in essence. So that's the slope. That's the intercept. So y bar or y hat, in this case, 199.059, let's say we stop here, x, plus 379.49, and we stop here, changes to 3. So that one is also given from technology. Find the best predicted value of y, which represents the metabolic rates. When x is equal to 1.3, the concentration of testosterone. We proved there is a significant linear correlation. Therefore, we plug in, meaning put 1.3 instead of x. Do the math. So when x is equal to this number, y hat is equal to 638.2697. Again, I'm using a lot of decimals. You have to really pay attention to the question to figure out how many decimals. Finally, using the above pairs and the value of R, what proportion of the variation in metabolic rates can be explained by the variation in the concentration of testosterone? In general, it is the value is R squared, everybody. So R squared is the answer. The proportion of the variation in Y can be explained. The Y by X can be explained by R squared, which is this number, or 98.69%. 98.69%.